Well, good morning to everyone. My name is Steve Drekic, and I'm in the same department as Cynthia. I want to thank Cynthia for the opportunity to come here and present today. What I thought I'd do is maybe before I get into the actual little lesson that I've planned for you here, just to give you a little bit of context about myself. A lot of you I know here, some of you I haven't met. A little bit about myself and about the types of courses that I tend to teach in statistics and actuarial science. So very briefly, if we take the field of statistics and we break it up into three main sort of categorizations, we could talk about data analysis, which is obviously pretty self-explanatory. It's a gathering, display, and summary of data. Something that's more closer to my heart is the theory of probability, which simply put is this mathematical study of chance, randomness, and uncertainty, those being the key words. And then sort of a combination of 1 and 2 is the idea of statistical inference, where you use data and the mathematical theory so that you can make conclusions based on data you've taken from a certain population. So I've already alluded to the fact that probability is near and dear to my heart. It's the type of material that I tend to teach from second year right up until fourth and graduate level courses. And if I had to simply define probability as a one-sentence description, then this is something that I might use here. We have a number of possible outcomes in a type of experiment, and what we're doing is we're trying to use probability to quantify, mathematically quantify, the likelihood or chances of those outcomes taking place. And one of the courses that I've tended to teach over and over again since the time that I've been here is probably my favorite course, which is Stat 333. It's a course that's a prerequisite for stat and axi majors, so it tends to be a fairly large class, and it's a course in what's called applied probability. So if we take a brief look at the course outline or the course description for this course, one of the main target areas that we tend to teach here is the introduction of Markov chains, both in discrete time and in continuous time. And so the topic that I've picked today is something that's a very important problem in the study of Markov chains. The idea of a random walk, or what I'm going to talk about today, is the gambler's ruin problem, very famous problem in probability theory. So let me describe the mechanics here of what's happening. So what we're going to consider here is we're going to put ourselves in the shoes of a gambler. So we're a gambler, we've got some money to spend, and we have a simple game. Okay, we play a game, and there's a so-called probability, we'll call it little p, which represents a probability of, saying, winning 1 unit or $1. And then there's a corresponding probability q, which is 1 minus p, of losing $1 or losing a unit. Okay, and so what we assume is that every time we play a game, the impact of a game doesn't impact any of the other games. So we assume that successive plays of this simple game are independent of one another. Okay. So the main interest in this particular problem is if I'm a gambler and I start off with, say, I dollars or I units, so think of I as some sort of positive integer, then I'd like to know the probability that I'm going to end up getting the whole jackpot, the whole amount of winnings, which will denote by capital N, also being a positive integer. And we keep playing this game until I either end up getting everything or I end up losing everything, which means I'm bankrupt. So one of two things can happen. I either end up with 0 or I end up with the entire jackpot, which is capital N. And starting with I units, I'd like to be able to determine, ideally, an explicit formula for this probability. Okay? So to get us started in that direction, we're going to let capital P sub I represent the probability that if I start off with I units, then I will end up with the entire jackpot. So I here obviously runs over the possible values from 0 all the way up to capital N. Now, one of the things that we do in Stat 333 prior to the study of Markov chains is we spend probably the first month of the course talking about basic probability rules, and in particular the idea of conditioning. Conditioning is a very important and useful technique in the study of Markov chains. So what we would typically do as a way to get started with this problem is we would condition on the outcome of the very first game. We're either going to win or we're going to lose a unit. Okay? So using the law of total probability, we can write that p sub I, in the one hand, if we do win, then our units are going to increase from I to I plus 1. And then, since the game is independent of the previous game, then really we're starting again, you could think of it as starting from scratch, but this time with I plus $1 as your starting point. And then we have the corresponding probability if we lose $1 or lose a unit, then we're starting off at I minus 1 for the second game. And this holds true for every intermediate value of I ranging from 1 up to n minus 1. Now, I've purposely excluded the two boundary cases, which are 0 and capital N, because those are easy to handle. Obviously, if you start off with nothing, then the probability that you end up with the entire jackpot is 0. Conversely, if we start with the entire jackpot, why are we going to bother playing anymore? The probability of winning the entire jackpot is 1. So those are our two boundary conditions. So what we'd like to do is we'd like to be able to work with, as our starting point here, this equation that I wrote down on the previous slide. Okay? And so if we look at the left-hand side of that equation, the capital P sub I, in front of that capital P sub I, it's invisible, but it's there, is the number 1. It's multiplying the P sub I. Okay? Now, if I'm trying to sort of figure out a way to solve this, by the way, most students don't know this. This is a second-order linear difference equation. Most students taking Stat 333 would say, huh? At that point. So if we knew that, we could basically write down the solution pretty quickly. But I'm going to assume that we don't know anything about linear difference equations, and we're going to try to solve this from scratch. So if we take that number 1 and write it in a slightly fancier way, 1 is nothing more than P plus Q. Right? It's just a fancy way of writing the number 1. Now, what's interesting about that is if I expand the left-hand side of that equation, I can write that as P times capital PI plus Q times capital PI. And what you notice is that things start to look very similar on left and right-hand sides. So if I just rearrange terms, so I bring all the values that have a common factor of P over to the left side and all the ones that have a common factor of Q on the right-hand side, then I can write this equation and solve for the difference of pi plus 1 minus pi in terms of a recursive relation where I'm multiplying by this constant q over p. Okay? So this is now the point from which I'm going to work with. Now, just as a test, let's plug in values for I into this equation and see what we get. So if we plug in the value of I equal to 1, we obviously get P2 minus P1 is equal to this expression. But if you look at the square bracket here, remember we said P0 is 0. So we can remove that piece, and this simplifies to simply be Q over P times P1. Let's do it for I equal to 2. If we plug in I equal to 2 into our equation, we end up with this difference, P3 minus P2. And now what you see is in square brackets, we have P2 minus P1, for which we could substitute the line previous. So if we make that substitution, lo and behold, we end up with now a squared term times P of 1. So if you continue this process, okay, you start to see a pattern emerging. Okay? So in general, inductively, if you use induction, you can show that pi minus 1 is nothing more than this ratio, Q over P, raised to the power I minus 1 times this unknown yet. We still don't know what P of 1 is, but just write it as P of 1. And we could do this process over until the last value, which is for I equals n minus 1. We end up with this particular equation. So we have these sets of equations at our disposal now. So what can we do with this? Well, let's take a look at these first set of equations from up to this point, pi minus 1. What's interesting here is if you add all these equations together, notice what happens on the left-hand side. You end up with a telescoping type of sum where the minus p, where the minus p2 here cancels with the p2 here, the minus p3 cancels with the p3 here. And so what you end up getting, if you add the first I minus 1 of these equations together, you end up with simply two terms on the left-hand side, P of I, and then minus the unknown P of 1. And what's happening on the right-hand side? Okay, well, if we look at the right-hand side, all that's going to happen is we're just going to add all these right-hand sides where there's always a common factor of p of 1 there. And so the rest of that ends up being a particular finite series, right? Now, if you swing the p of 1, which is on the left-hand side, the minus p of 1 over to the other side, you can group that term with the other terms and factor out that p of 1. And now you just have this extra term, which is 1, which you can rewrite as q over p raised to the power 0. And essentially what you end up getting here is an expression on the right-hand side which involves a finite geometric series. So again, I would ask my Stat 333 students, you guys all know the formula for the finite geometric series, don't you? And most of them would again say, huh? What are you talking about? Right? So I said, no problem. If you don't remember it, here's a quick fire way to remember it. If we define the term in square brackets, our finite geometric series, as capital S, okay, so we have this term on the right-hand side, and I want to know a formula for this, then if I multiply both sides of that equation by that ratio q over p, notice that every term basically increments 1 in terms of the exponent. And if I now subtract these two equations, then all the terms cancel on the right-hand side except the 1. And of course, this last term, q over p to the minus I. If I've subtracted these two terms, then I have this expression here. So now I can solve for s by simply dividing by 1 minus q over p. And that's a quick fire way to remember the formula for a finite geometric series if you're ever stuck in a bind, I guess. And that's what I tell my 333 students. So with that expression, we now can write p of I in terms of this unknown quantity of p of 1, and we can replace the finite geometric series with a nice closed form expression that we just developed. And this holds true for all I going from 2 to n, but it also holds true even for I equals 1. If you simply plug in, notice that when you plug in I equals to 1, you still get an equality. P of 1 is still P of 1. So it even holds true in the case of I equals 1. Now, one thing that I failed to mention here, but I'm going to, for purposes of completeness, I'm going to say that in order to use this formula or this method, I've assumed, obviously, that I'm not dividing by 0. So the q over p must not be equal to 1, which is just another way of saying that I'm assuming p can't be 50%. Okay? If p is in fact 50%, so we have a real fair game here, winning and losing, if p is equal to a half, then basically if I look up at my starting point here where the terms are all square bracket in that square bracketed term, if I replace all the q of p's by 1, then in fact, what am I doing? I'm adding the number 1 I times. So we get a very easy formula in the case when p is equal to half. P of I is nothing more than I times p of 1. Again, holding true for all I going from 1 to n. So good point now to recap or to summarize what we've obtained up to this point. So we have these two formulas depending on whether p is half or p is not a half. And now we recall what we want to do is we want to solve for p1, right? That's our unknown. But there's one piece of information we haven't used yet. And that is p of n is equal to 1, remember. So if we plug in p of n equal to 1 into our two formulas, then we can have an explicit way to solve for our unknown quantity p of 1. So if we do that, we end up finding that p of 1 in the one case is simply this expression that you see here. And obviously it's simpler in the case where p is equal to half. P of 1 is nothing more than 1 over n. So bottom line here, our final overall formula for the gambler's ruin problem is this very nice formula that you see here in the case where p is not a half, and very simply I over n if p is equal to a half. Okay? So at this point, to recap now, to sort of summarize, let me give you a fun numerical example just to demonstrate the use of this. And I thought I would use the following scenario. Let's consider the current world's men's number 1 and men's number 2 tennis players in the world. So these are the two guys here. I'm sure you guys are familiar with this if you're tennis fans. This is Novak Djokovic, the number 1 player, and Roger Federer on the right. These guys travel the world. They play many, many tournaments. And so let's create a scenario here where they're not able to go on the court. So what they're going to do is they're going to be, instead of playing ping pong in the locker room, they decide to have this other game. They're going to play closest to the wall. They're going to flip coins. Let's suppose they're in Canada for a tournament. They're going to flip loonies. They're going to stand a certain distance from the wall. They're going to flip, and they're going to measure the distance to the wall, and whoever's closest wins. Now, Roger's 34 years old, arguably the greatest tennis player of all time. Novak's 28. Roger's the more experienced guy. He's been around. He's played this game many times. Okay? So let's suppose that he has a better chance of winning, say 60% on each flip. So what we can ask is, let's say that we give Roger 5 loonies, and we give Novak a slightly larger number, say 10. Then what's the probability that Roger will wipe out Novak in this game of closest to the wall? Well, we can use our gambler's ruin formula, with our capital N being 10 plus 5, which is 15, and Roger's starting point is 5. We find that the probability is approximately 87%. Pretty high. So you might think, all right, let's give Novak a better chance. Let's give him a fighting chance. Let's give him double the amount of coins. Let's give him 20. But we don't want to give Roger a poor shake, so we're going to give him double what he had. Let's give him 10. So you might think that Novak's going to have maybe a better chance here because he's got more coins. But at the same time, he has to work harder because now Roger has more coins. And in fact, if you work out the formula here, you find out that there's actually a greater chance that Roger is going to win. There's now almost practically 100% chance that Roger is going to win this game. Regardless of the outcome, both guys are good sports at the end. Okay? Thanks, guys. I'm going to stop there.